So I'm Dr. Ryan St. Pierre. I'm a professor here at UB in the Department of Mechanical and Aerospace Engineering, as well as Computer Science and Engineering. I started in this research field working in microsystems first, and then I evolved working in microrobotics, and then eventually taking my engineering tools into biology. And so I brought a very fundamental understanding of physics, mathematics, dynamics and controls, and hardware into all of these domains to kind of bring together small-scale robots. So my lab focuses on hardware, particularly for small-scale robots, across mechanical hardware, electrical hardware, and computer hardware, and how we integrate that all together to make highly dynamic small-scale robotic systems. So when we think about the full robotic stack, which needs hardware for actuators, hardware for sensing, hardware to bring together software and the embodiment of the robot, my core mission of my group is how does that change when we make robots small, highly dynamic, and autonomous. So one project that we're currently working on is understanding the physics and dynamics of snapping shrimp. So snapping shrimp move their claws at incredibly fast speeds underwater to create a cavitation bubble, and they do this all highly repeatable. How we understand the physics and dynamics of snapping shrimp gets translated into jumping robots. And the other thing that we work on are how do we create fully autonomous small-scale robot systems. So one of the projects in my group is called Buffalo Bites. It's about a cubic inch fully autonomous robot which can navigate and move around the world, and if you look really hard, you can probably see a few hanging around other labs on campus. One of the main projects in my group on jumping microrobots is collaborative with external biologists. Particularly, I work with people who look at functional morphology, biomechanics, and evolution. And we take our tools as engineers to understand dynamics and mathematics, and how does that map onto an evolutionary phylogeny. So how do these mechanisms evolve? What are the physics that govern their behavior? And how can we translate that into robot systems? So my work isn't just on bio-inspired robots, but we use robotic platforms to understand biology better. So I think if we think about small-scale robots, we can kind of think about all of the capabilities of insects themselves. Insects are capable of accessing locations that are inaccessible to humans. So we can always do environmental inspection, we can do infrastructure inspection, but at the same time we can imagine these new ideas and new ways to use small-scale robots. So one thing that insects are really good at is utilizing their bodies to build infrastructure. And so we could think about sending teams of small-scale robots into space environments where they can use their own bodies to build infrastructure in space. We teach a lot of hardware classes across computer science and engineering and mechanical engineering. So for computer science and engineering, I teach digital systems, which is a core computer engineering class. And for mechanical engineering, I teach mechatronics. Both of these classes require integration and utilization of core electrical hardware that our robots operate on. So for example, I'm just wrapping up teaching digital systems and computer engineering, and we learned how to make hardware finite state machines that would govern robot brains. So we try to think about how do we use electronics to solve problems, and so how are we able to solve interesting robotic problems with hardware. So a lot of my students do work on building robots, but for us the robot is not the final product, the science is. So a lot of my students will build these robotic physical platforms to then test them to understand, forces, motion, and we'll use those data from the physical robot platform to then inform mathematical models. But almost all of my students end up getting familiar with how do we build a robot? How do we build a robot from scratch? How do we build the mechanical hardware? How do we design a circuit board? All of my students learn how to solder in my group. And so eventually they all get really good at working on the full robot stack, or at least the low-level robot stack, where they can do mechanical hardware, electrical hardware, and then just enough software to make our robots functional. So every February, my group participates in Engineers Week at the Buffalo Museum of Science, where we bring a whole bunch of our robots from the lab to go and interact with the general public, and mostly it's K-12 students. So we bring physical models of snapping shrimp, we bring our origami robots, we bring buffalo bites, and even this year we brought an interactive robot that has a face. And so we got to see how people engage with these different robots and are excited about the different aspects of the robots. And every year my students. So I think the best advice I have is to just reach out and get involved. I tell all of the students who come and meet me and talk about doing research in my group, and a lot of them, haven't had any experience doing robotics before. I tell them that that's fine. I actually didn't do robotics until my PhD. So even if they're doing robotics now as an undergraduate student, they're still ahead of me. So there's no bad time to get involved in robots. It's never too early and it's never too late. So these are some of the robots from my lab. We have a US penny for scale. So this one is our Buffalo Bite. It's about a cubic inch. It's fully autonomous and it even has onboard Wi-Fi and Bluetooth. And next to it is our Buffalo Bit, a smaller version of that robot. Over here are our jumping microrobots. We have jumping microrobots made out of super elastic shape memory alloy. We have soft jumping microrobots that use torque reversal mechanisms like snapping shrimp, and we even have a fully autonomous springtail inspired jumping microrobot, which has onboard computation, but you can only upload a program size of about 1 kilobyte. And then lastly, we have an interactive microrobot, which helps us look at how people engage empathetically with small-scale robots.